So welcome to this some deep dive in the core of the Nutanix distributed file system. So my name is actually Oliver Graf. I'm the partner system engineer for the Nutanix Switzerland. I'm at Nutanix since almost, or actually 1 year and 1 month. Before, I had experience with Sun Microsystem, 8 years, and 9 years of NetApp stuff. So, well, let's go first to the agenda. So, just a bit of an overview of the Hyperconverged platform. Then the second part is understanding the distributed storage fabric, then the I/O logic, how we do actually performance acceleration with our solution, and at the end, the fun part with the kickboard. You already have the link in the chat, so really please, if you want to win a kickboard, just fill in your name, address, so if you're winning the kickboard, we can send it to you. Good. So, Hyperconverged platform. There are actually a few core structures for hyperconverged systems that actually must fulfill. So when you look at the first part, actually it must converge and collapse the compute stack. So compute and storage should be in one box. The second, it actually must distribute data and service across nodes in the system. The third part, it really must appear and provide the same capabilities as centralized storage. So example would be HA and live migration. The fourth part, it really must keep the data as close to the execution as possible. So really hold the data as close as possible to the compute so that you have the lowest latency in the box. And then we have actually two shoulds. So it should be a hypervisor agnostic. So you shouldn't care what hypervisor is running on. And it should be hardware agnostic. Therefore, it shouldn't. You shouldn't care on which hardware you're running on, actually. So just to look at this picture, it shows a typical 3-tier stack versus a hyperconverged stack. As you actually can see, the hyperconverged system does the following. It does virtualize and move the controller to the host. It does provide core services and logic through the software, actually. And it distributes data across all nodes in the system and moves the storage local to the compute. So the Nutanix solution is really a converged storage and compute solution, which really leverages local components and create a distributed platform for actually running any kind of workloads on it. As well, each node runs an industry standard hypervisor and the Nutanix controller VM. The controller VM is what actually runs the Nutanix software and serves all of the I/O operation for the hypervisor and all VMs running on the host. So when you do a breakdown and a logical breakdown to one node, so actually the controller VM is therefore responsible for the core Nutanix platform logic and handles services like storage I/O and the transforms like deduplication, compression, and erasure coding. It has the UI and the API services, upgrades, DR, and replication, and a lot of more services that are actually running on the controller VM. Just a side note, some services or features will actually spawn additional helper VMs or use the microservice platform. Actually contain the containerization of an application. So, for example, our Nutanix Files deploys just a standard additional VM on the box, whereas Nutanix Objects will deploy VMs for the MSP and leveraging those. The question actually arises: why are we doing virtualizing a controller? Well, the key reason for running the Nutanix controllers as VM in user space really comes down to 4 core areas. So it's actually, the first one is mobility, so hardware and hypervisor agnostics. The second is resiliency, redundancy, and availability. Third part would be maintenance and upgrades, and the fourth part is actually performance. I'll come later on that. So, well, since the beginning, we knew we were more than a single platform company. In that sense, choices has always been a big thing for us, whether it is with hardware, cloud, or hypervisor vendors. By running as a VM in user space, it really decouples the Nutanix software from the underlying hypervisor and hardware platforms. This actually enables us to rapidly add support for other hypervisor while keeping the core code base the same across all operating environments. That means actually on-prem and cloud. So additionally, it gave us really flexibility to not be bound to vendor-specific release cycles. Due to the nature of running as a VM in user space, we can actually urgently handle things like upgrading or CVM failures, as they're really outside of the hypervisor itself. For example, if there is some catastrophic issue where the CVM goes down, so the controller VM crashes, the whole node still continues to operate with storage IOs and services coming from actually one of the other CVMs in the cluster. And as well, during Acropolis OS upgrade, that's the core software, we can reboot the CVM without any impact to the workloads running on the host. But the question isn't being in the kernel so much faster. That's always the questions that raises up. So simply, a simple answer would be actually no. It's a common discussion topic, the debate around being in the kernel versus in user space. Just to summarize, there are 2 areas of execution in operating system: the kernel privileged core of the OS where drivers may sit, and user space where application and processes sit. Traditionally, moving between user space and the kernel can therefore be quite expensive in terms of CPU and time, just because of the context switch. So the debate is that being in the kernel is always better and faster, which is actually false. So really bear in mind, no matter what, there always be context switching in the guest VM's OS. If you want to get really deeper in it, I would recommend actually reading the user versus kernel space section in the Nutanix Bible. That's just nutanixbible.com. You find there a huge section about that. And it covers both actually pros and cons of each. So talk about the distributed system now, actually. So there are 3 core principles for a distributed system. First, it really must have no single point of failure. The second part, it must not have any bottlenecks at any scale. So I have to really scale out linearly. And the third, it must leveraging concurrency. So together, a group of Nutanix nodes form this distributed system responsible for providing the Prism and Acropolis capabilities. All services and components are distributed across all CVMs in a cluster to provide for really high availability and linear performance at any scale, actually. Just the picture shows an example of how these Nutanix nodes form this Nutanix cluster, with the controller VM that are actually talk to each other, and you have the hypervisor, you have the user VMs, and the controller VM that actually controls the hardware and the I/O through the hypervisor to the VMs. As well, these techniques are also applied to metadata and data alike by ensuring metadata and data is distributed across all nodes and all these devices. We can ensure the highest possible performance during normal data ingest and read protection. This enables our MapReduce framework, that's the curator service that's running on the CVM, to leverage the full power of the cluster to perform activities currently. Sample activities include data read protection, compression, erasure coding, deduplication, and some other stuff. Good. Just an understanding of the distributed storage fabric from Nutanix. The Acropolis distributed storage fabric is designed to really simplify storage and data management for virtual environments. By pooling flash and hard disk drive storage across the Nutanix cluster and exporting it out to the virtualized layer as iSCSI, NFS, SMB shares, for example. So this really eliminates the need for SAN and NAS solutions, as I showed with the three-tier legacy architecture, as it is covered in this distributed storage fabric. So to go a bit deeper and how the DSF organize actually the data is through storage pool, storage containers, and vDisks. So when you talk about storage pool, that's a group of actually physical storage devices, including SSD and HDD devices across the entire cluster. And the storage pool spans multiple Nutanix nodes and is expanded as the cluster really scales out. Then we have the storage container. It's actually a logical segmentation of the storage pool and contains a group of VMs or files. Some configuration options, like the redundancy factors, are configured at the container level, however, are applied at the individual VM file levels. The container are typically have a one-to-one mapping with a data store. So really it is the container are direct the data store that I mount to either ESX, Hyper-V, or AHV. Then we have the vDisk. A vDisk is any file over actually 512 KB on the DSF, including VMDK files and VM hard disks. So vDisks are a logical compose of blocks which make up the block map actually. And just a side note to talk about the max size of a vDisk. So actually no artificial limits are imposed on the vDisk size on the DSF. The vDisk size is stored as a 64-bit signed integer that stores the size in bytes actually. This means the theoretical maximum vDisk size can be around 9 exabytes. But any limits below this value would be due to the actual limitation on the client side, such as the maximum vDisk size on ESX. So just a short overview on the structure related between various file systems in the DSF. So we have the vBlocks, we have the extend, and the extend group. A vBlock is just 1 megabyte chunk of virtual address space composing a vDisk. For example, a vDisk of 100 megabyte will have 100 times 1 megabyte vBlocks. vBlock 0 would be for 0 to 1 megabyte. vBlock 1 would be from 1 to 2 megabyte, and so on. These vBlocks map to the extents, which are stored as files on the extent groups, actually. So the extent is a 1 megabyte piece of logical contiguous data, which consists of n numbers of contiguous blocks that actually varies depending on the guest OS block size. Extents are written, read, and modified on a sub-extent basis for actual granularity and efficiency. So an extent slice may be trimmed when moving into the cache depending on the amount of data being read or cached. The extent group is a 1 megabyte or 4 megabyte piece of physical contiguous stored data. This data is stored as a file on the storage device owned by the CVM. Extents are dynamically distributed among extent groups to provide data striping across nodes and disk to improve actually the performance. The IO path and the cache. So actually, a typical hyperconverged storage IO path can be characterized into following core layers. A guest OS virtual disks. So this remains actually unchanged with Nutanix. Depending on the hypervisor, the guest OS will use a device driver to talk to the virtual disk device. On the hypervisor to Acropolis DSF, via the CVM, actually the communication between the hypervisor and Nutanix occurs via standard storage protocols over the local interface of the CVM and hypervisor. This would be iSCSI, NFS, or SMB3. At this point, all communication has been local to the host. So actually, there are scenarios where I/O will be remote. For example, when a local CVM goes down. I talk about data locality in a later slide, actually, just to show what I talk about. So then the Nutanix I/O path. This is all transparent to the hypervisor and user VM, and it's native to the Nutanix platform. The I/O logic. Well, within the CVM, the Stargate process is actually responsible for handling all I/O coming from user VMs and persistence. So when a write request comes to Stargate, there is a write characterizer which will actually determine if the write gets persistent to the oplock, extend store, or actually autonomous extend store. Similarly, for reads, the read characterizer is responsible to handling the reads and managing cache and read aheads. Just a side note about all-flash system. So in all-flash system, you don't have any storage tiering on the box that the ILM service will take. Because you have a full flash, you not have storage tiers there. The only storage tiers you have when you have a hybrid with SSD and HDD, or when you have a hybrid with NVMe and SSD. So let's talk about the oplock, actually. Oplock, extend store, autonomous extend store, and the unified cache. So the oplock is actually similar to a file system journal and is built as staging area to handle bursts of random writes, coalesce or actually merge them, and then sequentially drain the data to the extend store. So up on the right, the oplock is synchronously replicated to another n number of CVMs oplock before the write actually is acknowledged for data availability purpose, actually. So all CVM oplocks take part in the replication and are dynamically chosen based upon this load. The oplock is stored on the SSD tier on the CVM to actually provide extremely fast write I/O performance, especially for random I/O workloads. So if data is currently sitting in oplock and has not been drained, all read requests will be directly fulfilled from the oplock until they have been drained, where they would then be served by the extend store or unified cache. For containers where fingerprinting actually data has been enabled, all write IOs will be fingerprinted using a hash scheme, allowing them to be deduplicated based up fingerprint in the unified cache. The extend store is the persistent bulk storage of DSF and spans all device tiers and is extensible to facilitate additional device tiers. So-called actually cloud or external NAS storage, for example. Data entering the extend store is either being drained from the uplog or is actually sequentially or sustained in nature and has bypassed the uplog directly. So Nutanix ILM will so the information lifecycle manager will determine tier placement dynamically based upon IO patterns and will move data between tiers, therefore. And now the autonomous extend store is actually a new method for writing and storing data in extend store. It has been actually introduced in AOS 5.10, so it's quite new. It actually leverages a mix of primarily local global metadata, allowing for much more efficient sustained performance due to metadata locality. For sustained random write workloads, this will bypass the uplog and be written directly to the extend store using AES. For burst random workloads, this will take the typically uplog IO paths, then drain to the extend store using AES where possible. The unified cache. The unified cache is a deduplicated read cache which actually spans both the CVM's memory and the SSD. So upon a read request of data not in the cache, the data will be placed into the single touch pool of the unified cache, which completely sits in memory, where it will use least recent used until it is evicted from the cache. Any subsequent read requests will move the data into the memory portion of the multi-touch pool, which actually consists of both memory and SSDs. From there, the LRU cycle, one for the in-memory piece, upon which eviction will move the data to the SSD section of the multi-touch pool, where a new LRU contours is assigned. Any read request for data in the multi-touch pool will cause the data to go to the peak of the multi-touch pool, where it will be given a new LRU count. Just talk about a bit performance and acceleration. So DSF also includes a number of capabilities that enhance performance. So it has intelligent tiering, data locality, really important, VM flash mode, and shadow clones. So when we talk about intelligent tiering, this is actually only when you have hybrid versions, so NVMe SSD or SSD HDD. If you have a full flash, there is no tiering because you have a full flash system. So actually DSF continually monitors data access patterns and optimize data placement on either the SSD or HDD tier. Achieving the best performance without administering intervention. So you don't have to do anything. It's really the automatic process that AOS will take care of it. So there is no manual tiering possibility. All is been done by the operating system on the CVN. So the SSD tier provides really the maximum performance for hot data, so random IO, while the HDD tier provides maximum capacity and economy for cold data and sequential IO. So the point is, Nutanix hot data is always in the flash. It's always in the fastest possible tier. Only cold data will then move to lower tier storage. Now, data locality. Data locality is really a unique feature that Nutanix solution actually has implemented. So really being a converged platform, I/O and data locality are really critical to cluster and VM performance with Nutanix. As I explained in the I/O paths before, all read-write I/Os are served by the local controller VM, which sits on each hypervisor based on beside actually on the normal VMs. A VM's data is served locally from the CVM and sits on a local disk under the CVM's control. Now, when a VM is moved from one hypervisor node to another, the newly migrated VM's data will be served by the now local CVM. When reading now old data, the I/O will be forwarded by the local CVM to the remote CVM. All write I/Os will occur locally right away, actually. DSF will detect the I/Os that are occurring from a different node and will migrate the data locally in the background, allowing for all read I/Os to now be actually served locally. So the data will only be migrated really on a read as to not really flood the network. So therefore, with data locality, we could really reduce the network utilization on around 70%. And again, data locality at our point really does matter. As you see in that list, the cycles on a network are really not really good. So you should position your data as close to the fastest possible I/O device that you have. Then disk balancing. As well, DSF has a native feature called disk balancing, which is used to ensure uniform distribution of data throughout the cluster. Disk balancing works on a node's utilization of its local storage capacity and is integrated with the DSF Information Lifecycle Manager. Its goal is to keep actually the utilization uniform among nodes. Once the utilization has been reached, a certain threshold will step in to really do this balancing. So actually, this picture just shows an example from a mixed cluster after disk balancing has been run in a balanced state. And again, all this process is done fully automatic. Nobody has to actually care about where which data gets placed. And it always uses the cold data that he will move. He never touches hot data that is in the flash to move somewhere else. So storage tiering and prioritization. The disk balancing is about how storage capacity is pooled among all nodes in a Nutanix cluster, and that ILM would be used to keep hot data local. Well, a similar concept applies to disk tiering, in which the cluster's SSD and HDD tiers are cluster-wide, and DSF ILM is actually responsible for triggering the data movement events. So a local node's SSD tier is always the highest priority tier for all I/O generated by the VMs running on the node. However, all of the cluster's SSD resources are made available to all nodes within the cluster. So the SSD tier will always offer the highest performance and is a very important thing to manage for actually hybrid arrays. Again, bear in mind, full flash only have SSD, so we have actually just the first and the second step, and the third step is only when you have a third tier. So if you have a hybrid NVMe SSD or SSD HDD. Then just about the VM flash mode. VM flash mode pins actually specific VMs or vDisk to a cluster-wide SSD tier, so that the IOPS and the latency-sensitive workload can be mixed with other workloads in a single cluster without compromising on performance. VM flash mode gives a really fine-grained control over I/O performance. For let's say, for instance, all database transaction logs can be pinned in the flash, so they're always there in flash and never get destaged to the HD tier. Or, for example, all financial data can be pinned in a flash during a quarter end report. It's not a static, so you can choose, I have now reports that I have to take, a lot of read, I will pin the data in my SSD tier or flash tier. Then shadow clones. Shadow clones are actually significantly improve performance by caching virtual machines data across Nutanix cluster. So unique to Nutanix, shadow clones benefit scenarios where there are multiple VMs reading a single source of data, such as deployment servers and repositories. Actually, VDI deployments where many linked clones forward read requests to a central master are an idle example. So with shadow clones, Nutanix actively monitors vDisk access and trends. If there are requests originating from more than 2 remote controllers EVMs, as well as the local EVM, and all of the requests are read IO, the vDisk will be marked as actually immutable. Once the disk has been marked immutable, the vDisk is then cached locally by each CVM. So read operations are now satisfied locally by direct attached storage resources. And we are back at actually the data locality. So really hold the data as close to the computer as possible. And again, it's a full automated process. Good. Really, if you want to know a bit more deep in that, the Nutanix Bible shows quite a bit of information. So nutanixbible.com is really the Bible for Nutanix. You find everything in there of the file system, of the different software stacks that we have, and so on. So, well, let's go to the fun part. Hopefully I'll check. So we got a few more. To do it correctly, just stop sharing here. Good. So let's first do, oops, that. Then we say randomize. Okay, we have 9, huh? 9. Good. Let's see. 1. Who is 1? Virgin Alexander. Great. So actually, I will package the box and we'll send it to 45.
So are you available for some questions? I have one.
Yeah.
What is the typical distribution between SSD and HDD for typical clients, to get a feeling about this? Or is it fully individual?
It's 3-to-1 actually. So it's sometimes it's quite use case. But normally, let's say the HD tier is 3-to-1 to the SSD tier.
Okay.
But that's just, yeah, it's really depending on the use case, because it could be that they have quite a big work set, so we have to size it differently. But let's say best practice is 3-to-1.
Are there other questions from the audience? Sebastian wrote the question.
Look at the architecture. This system seems to favor read many, write few. Actually, yes. Actually, the thing is, as we are really have the data locality, it's quite less write on the network, because we write the data local to the node. So therefore, we really have the network utilization of less, let's say 70% of the network that normally occurs when you have, I would actually say, when you compare it with another vendor that does everything over the network, you will see always quite a big of network utilization, what we don't have. So actually, the answer would be, yeah, we really have to read many, write few. Any other questions? Nope.
Okay, then I'd say I would finish the official part, and thanks the presenters very much, and I stop the recording now.